Hello everyone, welcome to my presentation. I'm Huang from the group of Photogrammetry and Remote Sensing at Technical University of Munich. Today I will present the work about efficient estimation of 3D shifts between point clouds, which was cooperated with Dr. Yushen Xu, Dr. Ludwig Huegner, and Professor Stilla. First, we need to answer the question, why do we need to conduct shift estimation between point clouds? It's a simplified version of point cloud registration, which is useful for different applications. First, it's necessary for acquisition of full coverage of the scene. In practical cases, it's usually impossible to obtain complete observation of the entire scene by a single scan. To obtain complete observation of the entire scene, we need multiple scans as shown in the figure, especially for mapping large-scale scenarios. Meanwhile, when we try to compare multi-temporal point cloud datasets, point cloud registration is also required for temporal analysis, such as construction datasets as shown in the figure. It can help us obtain a full coverage over time. Additionally, they enable change detection and monitoring dynamics and progress. What's more, when we acquire point clouds from different sources, a common coordinate system is a prerequisite for fusion of the multi-source point clouds datasets, such as laser scanning and photogrammetrical point cloud. By fusing the multi-source data, the attributes of data can be enriched, and at the same time, we can increase the reliability and completeness of data. However, to achieve the aforementioned demands, there are still lots of problems when we try to align point clouds. For example, small overlaps, occlusions, and different views for multi-scan datasets. As for multi-temporal datasets, due to the temporal changes and dynamic objects, the acquired data often show as incomplete data with small overlaps. For multi-source point clouds, here we have an example. This is a forestry area. The problem is that the point clouds have various point densities, different measuring accuracy, and different penetration characteristics. To overcome these problems, we need to figure out the key points and provide our solutions. To conclude the aforementioned problems, two key points are needed to be addressed. First is noise and outliers. Second, how to deal with point clouds with limited overlaps. Here we provide our solution, which mainly consists of two main concepts. First, we use low-frequency components as correspondence, in which 3D points are transformed from the spatial domain to the frequency domain, and the unchanged parts of the registration pairs are treated as low-frequency parts. Second, instead of using local features, we utilize global features, which describe the entire point clouds using local distribution and densities of points. To be specific, the proposed method mainly contains four parts: discretization, which resamples on evenly distributed points. Then, in the transformation step, Fourier transform is conducted on these two signals to transform them to the frequency domain. Sequentially, shifts can be estimated by fitting the signals obtained by phase correlation using a robust estimator. Here is the general workflow of our proposed method. Then we will provide details of each step. In the voxelization and binarization step, the 3D space is resampled into a regularly resampled discrete 3D grid. Then the cells will be annotated with value 1 or 0 by the occupancy. Then, after the voxelization and binarization, the 3D signals will be converted from the spatial domain to the frequency domain by the 3D Fourier transformation. Then, by calculating the cross-power spectrum, the correlation between the 3D signals can be obtained, and then the parameters can be estimated from the cross-power spectrum. However, the cross-power spectrum is usually influenced by noise outliers or changes between the corresponding signals, which makes it's difficult to estimate parameters from the cross-power spectrum. Thus, we need to extract low-frequency components from the 3D signals. It mainly consists of two steps. First, we directly extract the center part of cross-power spectrum, which represents the low-frequency components in the 3D signals. By the way, after the extraction, a filtering is also conducted to further filter out noise in the correlated tensor. Finally, the shift can be estimated from the phase angle differences. First, unwrapping will be conducted on the filtered low-frequency tensor. Then we can see that the normalized cross-power spectrum can be represented by this function. The phase-different angle is actually a linear function of the shift parameters. Thus, now the task is to estimate the coefficients of the linear function. 3 coefficients corresponds to the shifts in the 3D space. The linear function can be estimated by a robust estimator. Then the 3D shifts can be finally calculated by the following equations. In the end, we finally obtain the shifts from the two signals. Okay, after the introduction of the proposed solution, let us have a look at how related methods perform in real applications. Here we will illustrate 3 different applications using the proposed shift estimation method, including building modeling using multi-scan datasets, forestry investigation using multi-source datasets, and street mapping using multi-platform datasets. The first application is the registration of multi-scan datasets. Here we selected 5 registration pairs from 3 benchmark datasets, including the Bahame, ETH2H, and the RASO datasets. All point clouds were acquired by terrestrial laser scanning. As illustrated in the figure, we can see that the walls and spines are well matched in the registration results using the proposed method. And then we also illustrate the other 3 registration pairs. We can see from the figure that it also shows very good results. The second application is the registration of multi-source point clouds. Here they refer to LiDAR point clouds and photogrammetric point clouds. The main challenges lie in 3 aspects. First, the laser penetrated the vegetation. Thus, LiDAR point clouds measured the terrain, while photogrammetric point clouds measured the tree crown. Second, the 2 point clouds have different point densities. The last point is that the data acquired from different platforms with different heights, which leads to a shift between the coordinate system of the 2 point clouds. This is also the reason why we need to register these 2 point clouds. Here is the registration results, and we also show the profile along the river in the valley. As shown in the figure, the 2 point clouds are well matched. The registration errors are less than 1 meter. The last application is the registration of multi-platform datasets, one by ALS and the other by MLS. ALS measured the roof of building and the road ground, while MLS actually measured the facade. It's very clearly shown from the profile across the road. The overlap is limited. This is the main challenge when conducting registration of these 2 point clouds. Here is the registration result of the 2 point clouds. We also illustrate the profiles perpendicular to ground and along the street. As shown in the animation, the ground and the roof are well matched. By the way, the registration errors are less than 0.5 meter. This experimental result proves that our method can produce satisfying quality of result under different situations. However, there are some limitations of the current work. First, we can evaluate the method with more high-quality datasets and test the dataset under different situations, such as different overlapping ratios and various scenarios. Second, in the current work, only shifts are considered. Whether it would be possible to extend the current concept to a full point cloud registration strategy with 7 degrees of freedom should be investigated. The further work can be conducted in several directions. First, deep learning techniques may help in learning features with better expression for registration. What's more, we can conduct further analysis based on the registration results, such as change detection and data fusion. Last but not least, there is a newly published large-scale benchmark dataset for registration, which is proposed under the cooperation of Wuhan University, FGI, and TUM. This dataset covers various scenarios. It can be a valuable data source for the task of registration, and here is the link for the benchmark dataset. That's all for my presentation. Thanks a lot for your listening and attention.